Hello to everybody. So today we will continue what we have done last time. We will speak about signals, and more precisely we will complete this alternate representation that we introduced. That was something about translating the representation of a signal from a function to a form of vector. Here you have an example of various signals which are kind of popular in electronics for many reasons. So you have the sinusoidal signal, the square wave, triangle, and sawtooth wave. So let's concentrate for a moment on the most simple signal we can think of in electronics, but not only, which is the sinusoidal signal. Okay, this is the chart, the graph of a sinusoidal signal. It's quite simple. So here we have the expression of the sinusoid. So as a function of time, A is the amplitude. Then there is the argument, which is an angle made of two parts, phi, which is a fixed part and it corresponds to the initial phase. So this thing here this, and then there is another part of the angle which is the part omega t, which is variable in time, and omega is the frequency, of course. Capital T is the period, which is the distance in time between two consecutive peaks or valleys or whatever corresponding points like these things. Omega is measured in radians per second. So omega, the units is radians per seconds, but sometimes the frequency is measured in hertz, which is cycles per seconds. See, cycles per seconds, and there are 2 pi radians in each cycle, so omega is equal to 2 pi f. Okay, this is useful to know. Quite simple. And I don't remember if I said that A is the amplitude. Okay, let's move on. So there is another representation of sinusoidal signals, which is what is called in electronics phasors. So it is related to the phase. What is this thing? So we define a real and imaginary plane like this. Here, imaginary plane, 2 axes, 2 dimensions. And then we consider this complex number here I use the Euler formula to express this number. And so we know that this number is a certain number z equal a plus ib. A is the real part and b is the imaginary part, and therefore we can plot it as a vector in this real and imaginary complex plane. A vector having a certain angle, which is the angle indicated here in this parenthesis, omega 0, which is a certain frequency, multiply t plus the initial angle phi. And because this angle depends on the time, it means that it's increasing with the time. So these vectors are rotating around the origin. As a convention, we consider rotating counterclockwise when we put positive omegas and positive increase in time. So those vectors here are rotating like this. And notice from the very beginning that there are also negative frequencies, meaning that if you put minus omega 0 here, omega 0 is just a number, you obtain vectors, which we call phasors in this context, that rotates at the same pace, let's say the same speed, but with different verse of gyration. And A is the amplitude. So we associate a complex number to a sinusoidal signal, and more precisely, we associate the real part of this complex number. So for instance, here you see a projection in this picture, let's say a geometrical graphical projection. So if you imagine the trajectory of a dot like this one, for instance, the red one, rotating like this with time, with the time, then you can imagine to project the shadow here, and if you call t time, if you call this axis time, then you will see, of course, the development of a sinusoidal signal with the corresponding amplitude and frequency and phase and so on. Here you have a more complete representation, in the sense that those two axes, for instance, this one is the real, this other one is the imaginary, it can be vice versa, it's just a convention that we can do, and this is the time. So here you recognize again the amplitude of the signal, the period, which is the distance between this point and this point, which is 1 over the frequency measured in hertz, and so therefore we know that omega is 2 pi f. This frequency omega, in order not to be confused with this other frequency f, is sometimes called pulsation. Okay, now the idea. The idea is that, as we anticipated, we want also to deal with non-sinusoidal signals, which means for us, let's say, any signal, like a signal like this. So this is whatever signal, time f of t. The idea is that under certain hypotheses, we can represent a signal as a superposition of sinusoidal signals. So what we are going to study is the so-called Fourier representation or Fourier transform of a signal, which is something that have been developed by Fourier a couple of centuries ago. So how do we do this? Well, now we have all the ingredients ready in order to cook this recipe. We have to do a couple of things. So we have to consider our function of time, f of t, as a collection of its own samples. So as we said, we collect the values of f and we put them in a vector. Here we have a column vector. We can do as well the same thing for a row vector, but now we do this with column vectors. So here you have the values. So you have the value of f at the time t equals 0. I call this sample 0 as 0. The value of f at the time delta t, I call this value sample of delta t, and so on. After the time 0 and before the time 0. This is what is written here basically. Then we go a step further and we consider what we can call continuous representation limit. So we said we have a vector now, and therefore we can think of computing the magnitude of that vector by doing this. This was the inner product, also with this extension to complex numbers, because here we have this star, the complex conjugate, which means that these are values of f, and each of those values, for each of those values we take the complex conjugate, and this gives us the square of the magnitude. So let's see better what is this thing. We have to go here. We write the definition, so we compute this summation. And then we consider one possibility, which is that this delta t, now it's a label, which is just labeling every sample of the function, but we can label them in a way that, we can sample them in a way that this distance between the two samples is small, is very small. So small that we can think of making it infinitesimal. So if we go to the continuous limit, this summation becomes an integral. Then those terms sk delta t, k spans from minus infinity to plus infinity, for instance, so all the possibility for this k delta t time instance, those were the values of f at a specific time instant t, and so basically they are f of t. So we consider this type of integral for continuous functions as the extension of the magnitude of the function, with this idea of vectors in mind. So here comes our complex exponential function. We said that in order to represent a vector, we need a reference frame. We need the axis, so we need a space, a vector space to put it. So we need to define a vector space also for functions. So the vector space is made of vectors, but we think of vectors as functions and vice versa. So we need to choose some functions that are good to be the basis of a vector space. Those functions that we choose as basis have to have some properties. One good property they can have is that they should be orthogonal and they should be unitary. So those vectors corresponding to those functions should be orthogonal each other and also have a unit length. So by orthogonal each other, we know what this means in terms of geometry. So how can we extend this to the world of functions, we can take advantage of the inner product. We said that if we have two vectors whose inner product is 0, then it means they are orthogonal. So if I find two functions where with this extension of inner product I find that their inner product is 0, then I give the meaning, the new meaning of orthogonality to those two functions. So now I, let's say, cleverly choose a particular class of function. I choose the complex exponential because they have this nice property that is written here but we don't demonstrate. If I choose one complex function with a frequency omega 0 and another one with a frequency omega whatever but different than omega 0, and I compute this thing, which is the integral we have seen in the previous slide, then this integral is 0 if omega is different than omega 0 for whatever omega and omega 0 different each other you take. We know that the magnitude of this thing is 1, but we can write this in this way by making use of this function delta, which is a sort of extension of the Kroneker's delta symbol that we already met. And it's a sort of extension in the sense that it works in the continuous case with this property. So delta is not a function, mathematically speaking, but it's a distribution, which is something that has a definite meaning only if integrated inside, together with another function. And we can represent it like this. Here you have a chart. So this is the Dirac's delta. It's a function that stays 0 for omega different than omega 0, and it's not 0. Actually, it's a sort of spike that goes to plus infinitive for omega equals omega 0. For us, it means that this inner product is different than 0 if omega equals omega 0. So if we are taking the inner product of a function with itself, we take something different than 0. Otherwise it's 0. And here we have a coefficient that comes from, let's say, this exact mathematical calculus that we can do. So those functions are all orthogonal each other. So they are good as a reference frame in order to decompose other functions and represent them in a vector way. So how do we do this? We do this by calculating the projections. So here aside, I try to make a small drawing. No, actually I can make it bigger, because I can try to zoom it a little bit, but I wanted to stay on the same page. So we have spoken about a simple two-dimensional example, x and y. Then here we said, okay, let's consider a vector. I can call it A. Then we consider the projections, AX. Here we have the unitary axis UX. It's a vector. I put an arrow like this on the head of it, so we can distinguish the vector from the length of the projection. Similarly, we can do this. Here we have the vector UY, and the length of this projection, we call it AY. This is the vector A, and we said that the vector A is a little bit, which is the length of the projection, multiplied the direction, plus a little bit, which is the amount of the projection, multiplied the other axis, the parallelogram rule. This is the same thing that we want to do here. So we consider the projection of our function onto an axis which is labeled by omega. So this means considering something like ax, or if you prefer, let's call it a omega, for every possible omegas. So this one you see here is not one equation. So these are many equations, one per each omega. So we consider this projection, we can compute it. Now we know how to compute this because it's the integral that we have seen so far. We just replace the functions here, and then there is also a coefficient of normalization, let's say. And so out of an integral, out of every integral we can compute, we obtain a single number, and we call it capital F, which depends on omega. So if we consider the collections of all those numbers, capital F depending on omega, then we have a function f of omega, and this thing is called the Fourier transform of f of t. F of omega is the Fourier transform of f of t. So it's the collection of all the projections of the function in every possible axis. And for us, the axes are complex exponential functions that we know are connected to frequencies. So once we have all those coefficients, we can do the opposite. We take them, we multiply by the vectors which are building up our basis, our reference frame, and then we summate all of them together, because this thing, maybe you see better like this, which is an inner product. It means that we have to multiply this by this and summate, but for summation we mean integration, because it's a continuous function. By doing this, we are basically repeating the parallelogram rule for summation. So what we did here, we do this here, but in many dimensions. So actually an infinitive number of continuous orthogonal dimensions. And the result of this, as we know with the rule of the parallelogram, should be the vector itself. And the vector itself for us is the function. So this operation is called inverse Fourier transformation, which is the synthesis of a function of time taken by summating many sinusoidal signals. Remember that these are sinusoidal signals basically, all of them coming with a certain coefficient. So this coefficient, we need to stress this point, f of omega, is a complex number. Why is a complex number? Because it comes from an integration where here we have a complex function. So generally speaking, this thing, the integrand of this integral, is a complex number, and so also this thing is complex. So to say it better, omega is a real number, but f of omega is a complex number, which means it comes with a real and imaginary part, or if you prefer, with a magnitude and a phase. The magnitude would be the magnitude of this unitary frequency we put here, and the phase of this f of omega is the initial phase of this function, sinusoidal, let's say complex exponential function we have here. So here we have a diagram that tries to explain why we want to do this. The reason is quite simple, and it relies on the fact that sometimes we have a problem we want to solve, and this problem is expressed in a way we call time domain. So we want to see how, for instance, a function evolves in time according to certain equation we have. For us it would be equations related to our circuits. We want to find the solution, but this path here is hard because the function is quite complicated. It's not just a simple sinusoid. Remember, for instance, the very basic example of recording the temperature in a room. Not all the time, of course, the temperature goes with a sinusoidal profile. It can be whatever in general. So the idea is that we develop methods to study our system in a simple regime. For instance, the sinusoidal regime. So we do the Fourier transform and we break one complicated problem into many but simpler problems. So we decompose the function into sinusoids, and then we have to deal only with sinusoids. So if we know how to work with sinusoids, then we are here, we transformed our problem, then we know how to do things with sinusoids, we do the computation of our problem for every sinusoid, and then if there is a big if we can summate all the results and recompute the synthesis through this inverse Fourier transform, then we turn around our initial very difficult problem and we reconstruct the solution. So this is possible if the system is of this type: linear, time invariant. So systems for which this thing is possible are called LTI, linear time invariant. These are systems for which the rule of the superposition of effects is valid. And fortunately for us, let's say maybe not all, but most of the circuits in electronics are systems that have this property, and therefore we can take advantage of this method to analyze those circuits.